Now going to draw a lot of graphs. Now if you've got two colors, that will make it a lot easier. If you have something like red and blue or whatever you've got at hand, use that. Now I'm looking at the equation. First thing to do, write the KC expression for me. Right. So this should be old news, right? C to the third times D divided by A squared times B. Is there something that I must leave out? No. No solids, no pure liquids, we're fine. Right, now just remember, the concentration was moles per volume. So if you can put it up there somewhere, just remind yourself how to think about this. Right, concentration, moles per volume. Okay, and they give me a delta H. What should I read from the delta H being smaller than 0? Forward reaction is exo. Forward reaction is exothermic. Right, now the reason why we do it in the table is I hate writing. You're lazy as well, hey? Right, so we'll get along fine. We're doing it in the table because then all the little lines, the little longer explanations are already there and you can just fill in. So let's see if we've got a better focus. Right, let's move on. Now, with the first one, I'm telling you, I'm putting A and B into a container. What do you have to remember? If they tell you they put A and B in, they're not putting C and D in. Right, they're not putting C and D in. Now you're going to be upset because this is the way to answer that first column. Nice, okay. This column is all about applying Le Chatelier. And when does Le Chatelier apply to a system? Only if there was equilibrium and I disturb the equilibrium. Now, if they only put A and B into the container, there was no equilibrium before. So Le Chatelier is not part of this. Right. Now we're just going to draw the graphs. So let's look at the first one, rates of reaction. See if I can put more of that in there. Right, still big enough for the guys at the back? You're fine. Good. Right, now, if I only put A and B in, I said there's a lot of this and the forward reaction can happen fast. So choose a color for your forward reaction and the forward reaction will be happening fast because the concentration of the reactants is high and the forward reaction will go fast. Then, reading between the lines, they did not put any C and D into this container, so the reverse reaction has got a rate of 0. And what happens is, as time goes by, this will decrease and that one will increase until they get the same rates. Why does this one decrease? Because as the A and B are being used, that concentrations will decrease and therefore the forward rate will decrease. This one increase, why? We started out with 0 because there was no C, no D. And now as the forward reaction happens, it produces C and D can start going back. And then that will increase. Right, and once they've reached the same, then we have chemical equilibrium. The rate of forward is equal to the rate of reverse. Now, why isn't the rates changing anymore? Once they've reached that stage where the rates are equal, it means, if you look at the equation, if the rates are equal, it means for every A that is being used in the forward reaction, there is an A produced in the reverse reaction at the same rate. So that means the concentration of A is not changing anymore. And therefore the rate of the forward reaction is not changing anymore. So the concentrations and the rates now stay constant. And this is chemical equilibrium. Right, chemical heaven. Everything is where it should be. Right, let's go on with concentrations. Now, I told you I put some A and B in. I didn't give you numbers. We're not going to look at numbers. We're just going to look at going up or going down. Right. So just choose. Put in some A and B into your container. And don't put in any C or D into your container. Right, I only put A and B in there, so what's going to happen? The forward reaction is going to happen, and what's going to happen to A and B? They will decrease. So A will go down and B will go down. Now, I'm going to do something a little bit difficult with this first one, and then make it easier afterwards. If you look at this, if the forward reaction happens, it will use 2 A's when it uses 1 B. So if A is going down, let's say it was on that right, and it's going down 2 units, we don't have any units, but say if it's going down 2 millimeters or whatever, what will happen to B is B will be going down from where it is just 1. Because 2 A's is using with 1 B. So A will be dropping 2 units, where B will be dropping just 1 unit. Right, and what will happen to C and D up there if you are using A and B? It is because you are producing C and D. So C and D should go up. How high should C go? 3 units. And D just 1 unit. And then we've got chemical equilibrium. And what do you know about chemical equilibrium? Then the concentration stays constant. Yes. Thanks. Right. When you've got chemical equilibrium, the concentrations are now staying constant, constant. Right, so Le Chatelier had nothing to say about what we did now. Now we're starting with Le Chatelier. We've got equilibrium, and now we can do something to the system. Now, the first thing we're going to do to the system is we are adding A to the system. What is the disturbance? If I add A, then the disturbance is the fact that the concentration of A is increasing. That means, according to Le Chatelier's principle, the system will react to do what? To decrease A. How can it decrease the A? By favoring what reaction? All right, by favoring the forward reaction. Now, the question, if this is for money, what's happening to C? If I favor the forward reactions, the concentration of C will increase. It will increase. Kc value? Same. No temperature change, no Kc change. Nice. So this is what you would have written down if you had a long answer, but now we want to draw the graphs. Now what did I do? I added A, and the moment that I added A, I gave the forward reaction bigger concentration of reactants. So the moment that I add A, the forward reaction would be very happy with what I'm doing. If I added A, right, the forward reaction will have more particles that can collide per second, so you'll more effective collisions, it's going faster. So adding A makes the forward reaction faster. Did I add any C and D at this time? No. So the C and D rate will still be where it was. That didn't change. Right. But they are very nice. They split the difference, eh? The one that's acting faster is making more product, and that will be increasing the reverse reaction, and always they end up splitting the difference and ending up halfway. Well, not necessarily halfway. Right, so what we had here, we added A. Adding A made the forward reaction faster. So at that moment, the forward reaction is faster. But because it's faster, it's producing more product, and eventually you'll have less A and B, that's going a little bit down. You have more C and D, that's going a little bit up, and you get a new equilibrium, right? Now let's go to the bottom one. Now always remember this, what happens at that moment, and then what does the system do? How does the system react? So let's start off by what's happening at that moment. I'm adding A. So how will I show adding A on this concentration graph? Adding A. At that moment, A is increasing. Right, at that moment. Now up there we said the forward reaction is favored. If the forward reaction is favored, what's going to happen to A and B now? It's being used. It's going to decrease. And C and D is being increased. So A and B will decrease, and it is bigger gradient, smaller gradient until it gets to 0. Bigger gradient, smaller gradient until it gets to 0. And if A and B is being used, then C and D is being produced. Bigger gradient, smaller gradient, 0. Bigger gradient, smaller gradient, 0. Right. Sorry, thanks. So always remember, you have to think what's happening at that moment, and then what's happening when the system reacts. At that moment, I'm adding A. There A's go. Right. But what does the system do? The system reacts to decrease A. But it cannot only decrease A. If it's using A, then it's using B as well, and it is producing C and D. So they will always do the opposite, the reactants and the products. Next one, B is removed. What is the disturbance? Yes, concentration of B decreases. Right, according to Le Chatelier's principle, the system reacts to increase the B concentration. How can it increase the B concentration? By favoring the nice reverse concentration, reverse reaction. What will that do to my C's? Reverse reaction, if the reverse reaction happens, it's using C's, so the C's will be less. Not good for your company, eh? Right. Kc value, same as before. No change in temperature, therefore no change in Kc value. Okay, now we're looking at this. If I remove something, if I make the concentration slower, what's going to happen to the rates of reaction? Is the rate going down or is the rate going up? Going down. If the concentration goes down, then the rate goes down. Right. There's less particles, less effective collisions per second. Down. Right. Now, if I'm removing B, am I slowing down the forward reaction or am I slowing down the reverse reaction? I'm removing B. I'm making the forward reaction slower. I'm taking its stuff. It can't happen as well. Right? If I'm taking B, then the forward reaction is going to be slower. So at that moment, if I take away B, the forward reaction rate is going down. I am taking away B, I am making the forward reaction slower. Did I remove any C's and D's at that time? No. So the rate of the reverse reaction is still where it was before. But then they split the difference. No, nice. And remember, it always starts with a bigger gradient because there's a bigger difference in concentration. So there's a lot to change, and then it goes less. Right. It's always bigger gradient, then going to a smaller gradient. Right, the one at the bottom. Remember, we have to talk about what happens at that moment and then what happens afterwards. Now, what happens at that moment is I remove B. How am I going to show it over here? Remove B. B must go down. The concentration of B decreases. If I remove B, then B has got a lower concentration. And then the system reacts. And the system makes new Bs. So B is going up a little bit. Right. But if it's making Bs by doing the reverse reaction, it's also making As. And what's happening to C and D? It must do the opposite. I can only make A and B if I use C and D. So they are going down. And now I don't care about 2s and 3s, ups and downs. Just get up and down. Hey, don't worry about going 2 up and going 3 down or whatever. Right, now the next one should be easy. Now the next one is just one more. Now I'm adding D. So when you're looking at Le Chatelier, the disturbance will be the fact that the concentration of D increases. Then, according to Le Chatelier's principle, the system reacts to decrease the concentration of D. How can it decrease the concentration of D? Which reaction must be favored? Nice, reverse reaction. What will that make happen to my to C? If I want to sell C's, this is bad news because the concentration of C is going down. And what's happening to the Kc value? Nothing. It stays the same. Right, let's go to the bottom. Now, if I add D up there, which reaction will be very happy with what I'm doing? The reverse reaction. If I'm adding D, I'm making the reverse reaction faster because I'm giving it more particles to collide, more effective collisions. Right. So the moment that I add D, the reverse reaction will be the one that is at that moment favored. It's going faster. Right. What's happening to the forward reaction? Well, at that moment, nothing, but eventually they sort it out. Right, guys, now draw the bottom four. Let's see if you're all right with this one. Finished already with the bottom ones. Right, so what had it? We added D. At the moment that we add D, obviously the concentration of D must increase. It's going up. And if the concentration of D increase, now the system is reacting. If I put something in, it's going to try to make it less. So if I put in D, I'm favoring the reverse reaction. So C and D will decrease because it's being used. A and B will increase because it's formed. Right. So C and D will be decreasing, going a little bit down. And A and B will be increasing, going a little bit up. And never mind about the relative heights. You might be out of the graph at the top or down at the bottom. It doesn't matter. Just get the shape of the graphs. So A and B is going up, and C and D is going down. And they will always do the opposite, the reactants and the products. Right, so now we're moving on to the more difficult ones. What was important here is if you look at the rate graph, if you look at the rate graph here, if I add something or I remove something, I only influence one reaction. If I take something away, I'm making one reaction slower. If I'm adding, I'm making one reaction faster. Now we're going to work with volume and temperature, and there we are influencing both. So this is going to change. Are you fine with this part? Right, let's move on to the more difficult ones. Now, if the volume is doubled, now, if I want to talk about Le Chatelier, I have to talk about pressure. Remember volume now with pressure. If the volume is doubled, the pressure will decrease. Nice. Okay, what works nicely is if you can take these last three rows, the next 3 rows, and just get it into two different ones, because I have more to write down than just what there's space for. If I decrease the pressure, the Chatelier's principle tells me the system wants to increase the pressure. Now, how can a system increase pressure? Come on, how does it exert pressure? Yes, moles of gas. So you make more moles of gas. Make more moles of gas. If you make more moles of gas, it will exert a bigger pressure, and that's what we're trying to do. And now, how do I know how to make more moles of gas? I go back to my equation. On this side, we had 3 moles of gas, and on that side, we had 4 moles of gas. So if I want to make more moles, which reaction do I have to favor? Nice, forward. So I'm going to favor the forward reaction, which will produce more gas, which will exert more pressure. Right, if I do this, will it be good for sales of C? Yes, I'll get more of C. And how about my Kc value? Nice, should stay the same. I've got no temperature change, so there should be no change in Kc value. What's happening here is when you change the volume, you are changing all the concentrations, right? So now this answer will be wrong, but the system will move it until you get concentrations that will give you the right answer. So you get the same Kc value. Right, let's go to the bottom. Now this, to me, this is the more difficult part. Now we've looked at volume. We said the volume doubled. If the volume doubled, what's happening to my concentration? What's the relationship between volume and concentration? Inversely proportional. Nice. So if the volume is doubling, then immediately my concentrations will halve. Right. My concentrations will halve. Now, if the concentrations decrease, now tell me, which concentrations are going to decrease? Is it this concentrations or that concentrations? The volume of the container was changed. So all the concentrations changed. Eh? They both, all 4 of them are in the same container. So if the volume doubled, then the concentrations of every single one halved. Now, let's look at the bottom graph. What will it look like here? This one, now we're over this half, but if it started out as 10, then obviously it will have to drop to 5. If it started out as 8, what will happen? It will drop to 4. If it started out as 4 or whatever, it will drop to 2, and if it started out as 2, it will drop to 1. So every single one, if the volume is doubled, the concentration is halved. So at that moment, every concentration is the half of what it was, because the volume is doubled. It's difficult, eh? Because you have to remember they're all in the same container, so the moment that the volume doubled, all the concentrations fell to half of what it was before. Okay, but now the system is reacting, and it is favoring the forward reaction. Now, if the forward reaction is favored, what's happening to A and B? It will be decreasing. So A and B will be going a little bit down. It is decreasing, going a little bit down, until we reach equilibrium. How about C and D? Well, if A and B decreases, then C and D should increase. And remember, bigger gradient and it becomes smaller. Bigger gradient and it becomes smaller. Right. As they sort it out, then it goes to constant rate, constant concentrations. Right, now we still have the top one to draw. Right, we had equilibrium, everything was fine, we had equilibrium and we came there. Now, the moment that we doubled the volume, what happened to all the concentrations? Halved. So the concentrations on that side halved. What will happen to the forward reaction? The rate will decrease. So the forward reaction has to go down. But what happened to the concentrations of C and D? They're in the same container. They also decreased. So what will happen to the rate of that reverse reaction? It will also decrease. And this is the first strange thing that you have to see. They both have to go down. Because both of the left and the right-hand side concentrations decreased when I changed the volume. So they both have to go slower. The question is just, who's the slowest, sort of? Now, let's go back. Go back to the first one. Here we said forward was favored. What does it mean if they tell you something is favored? It's faster than what? Not faster than before, faster than the other reaction. So if forward was favored, go down there and you will see forward has got the bigger rate. Right? If forward is favored, it means that it's got a bigger rate than the reverse reaction. Because we're going to use that sometimes when they ask you, they give you a graph and they ask which one is favored. The top one is favored because it's got the bigger rate. Right. So if forward was favored, forward is at top. If reverse is favored, then reverse is at the top because it's got the higher rate. How about reverse? At the top. Now, which one should be at the top? Forward. So reverse is the one that goes way down and then eventually come back, and forward just went a little bit. So forward is still at the top. It's just that both of them dropped, and then forward is faster than the other one. Right, is it difficult? But if you think about it the right way, then you're fine. If you're working with volume and you're working with Le Chatelier, you have to think pressure. Right. But when you get to graphs, you have to think concentration. So if the volume doubles, the concentration half. All the concentrations. So they must all go down. Right? And if the concentration decrease, then it's concentration on that side, and both the rates must decrease. It's just a question of who's going to decrease the most. Are you happy with this one? Right, so you have to practice this one. This is a difficult one. Eh? Right, let's go on to temperature. If I increase the temperature, easy. Then the system wants to decrease the pressure. How can it, temperature. How can it decrease the temperature? By favoring? Yes, endothermic. Right, it will favor the endothermic. And how do I know which reaction is endothermic? Go back to delta H. So you check your delta H, and that will show you forward reaction, exo. Okay, so if I want to do endo, then I have to do the reverse reaction. Right, what's going to happen to C? If the reverse reaction happens, I will have less of C. What happens to the Kc value? Well, think about products and reactants. If I have the reverse reaction happening faster, the products will be less and the reactants will be more. And both of that will give me a Kc value that is less. Right, so check. No temperature change? and then you go and see what's happening to the Kc value. Right, now we want to draw the graphs. Let's start with the top one. If the temperature increases, is the rates of the reaction higher or lower? The endo or the exothermic one? Aha. What did we say right at the start? Do you remember right at the start? We said if you increase the temperature, both endo and exo is faster. Right? If I ask you, how can I make this faster? You don't ask me, is it endo or exo? You just say, increase the temperature. Right. So the important thing is they are both faster. So what I want to see is both going up. The question is just who's going higher. They must both go up. There's the catch. If I increase the temperature, both rates are going up. Right, and now I want to know who's going the highest. How am I going to decide? Look at which one is favored. Reverse is favored. So reverse must be at the top. Okay, so let's quickly go back. When we had adding or removing, you only influence one rate, right? Only one went up or one went down. But once you have a volume change or a temperature change, they are both going up or both going down, right? You have to look at both of them. Right, let's draw the concentration graph. What's happening at that moment? Now with the previous ones, we either added or removed something which changed the concentrations, or we changed the volume which changed the concentrations. This time we're changing temperature. What's happening to concentration at that moment? Nothing. It's staying constant. No change at that moment, right? But now the system is reacting and we're favoring the reverse reaction. What will the reverse reaction do with A and B? It will produce A and B. So A and B should now go a little bit up. And if the reverse reaction is favoring, we are using C and D, so C and D should be going a little bit down. Right, now the next one should be super easy. Hey? We've done it the other way around, let's do it. If I decrease the temperature, then obviously the system is going to try to increase the temperature by favoring the exothermic reaction. How do I know which is exothermic? I check my delta H value, which tells me that the forward reaction is exothermic. So the forward reaction should be favored, which should give me more C's. Good for business. Right, and my Kc value will increase because I've got more products and less reactants. Right, let's get to the graphs. If I decrease the temperature, what happens to rates? The rates decrease. So they're going down. I just want to know which one is going down lowest. Right, they're both going down. I want to see both of them going down. Now, which one is favored? Forward. So forward is only going down a little bit. Reverse is going down a lot. Right. So if reverse is favored, it should have the bigger rate. If forward is favored, that should have the bigger rate. Right, and at the bottom one, once again, nothing at that moment. Changing the temperature does nothing to the concentrations at that moment, but now the system is reacting. If it's favoring the forward reaction, A and B is used, their concentration should go down, and C and D should go up. So A and B will be going a little bit down. C and D should be going a little bit up. Right, last column. Now, if you look at the catalyst, if I added the catalyst, now actually this one should be dark as well. What does the catalyst do? It doesn't influence my, my equilibrium, right? So we're going to end with the same Kc value. And what I want you to write in there is I want you to write down that, remember, that both reactions are equally faster. Equally faster. So their rates increase with the same amount. So if the one increase that much, then the other one should increase with the same amount. So the rates increase, but the important thing is they increase with the same amounts. So it's going to look like this. And therefore the concentrations are staying the same. The forward and the reverse are still happening at the same rate. You're not producing more reactants or more products. It's the same. Right, so actually you should be able to go and practice it on this page now.